Hi everyone. First of all, I am actually the native Russian speaker, so don't judge me hard. I'm in Armenia for 2 months, so I'm already working at Unum. So all the results that we will discuss today, it's the result for 2 months of work. So the agenda for today is here. Yeah, the first question is, the first point is why we even decide to speed up language model. The second is how we do that. The third is our experience in 2 months that we have, and our future plans, and a little demo that everyone can do by themselves. So yeah, the motivations. So every computer vision engineer and solution are trying to accelerate their inference, so the usage of neural net. So why NLP guys don't do that? Nobody knows. When I was working in Sberbank, we actually got the batch size of 1 for GPT-3, maybe 2, and that's it. Nobody was interested to accelerate the inference, but that's actually significant for encoder part of transformers, for natural language understanding. So yeah. At Unum, we are trying to do the universal search. What does it mean? We are trying to make any data domain, like text, like image, like audio, video, maybe HTML file or something like that. We are trying to make the search and to take all the data domain as the query and as the response. So yeah, we need fast inference. And we want to rebuild the index of this search engine in fly. So whenever we get the data, the new data from the user in their data for our database, we need to reconstruct the search engine, the index. So yeah, we need to do that fast. Actually, the fast encoders like VES or something like that is also need to be that fix it. In recommendation system and question answering systems. So yeah, that's how the universal search engine looks like. You can write the textual query and get the images as a result. So yeah, how we make the encoders faster. The first one, the first approach is quantization. The second one is specification pruning, the distillation, and optimized ML compilers. We will focus today with the first three, but I think more about quantization, the today topics. So, yeah, what is the quantization? It's easy to think about it like you just round the number with, you have the floating point number and you just rounded it. So yeah, you will have less bits to use, and this, that produces the less computation and less memory usage. So yeah, this is data type. So it's actually easy and safe to quantize from float 32 to, for instance, float 16 or vfloat 16. But it's a bit tricky with int 8 and so on and so forth, because you can significantly lose the accuracy. So yeah, there's lots of types of quantization. We'll discuss 3 of them. The dynamic quantization, that's the quantization where you try to change your weights in neural net inside the inference loop. So when you infer the model, when you use that, when you try to get the embeddings, you change the weights. So, but that works only for CPU. For us, it works only for CPU. So we don't recommend that, probably because we are more focused on GPU inference. And there's 2 types of static quantization. The first one is post-training quantization, or this is the type of quantization when you just take your weights of neural net and you just change numbers. And the second one, also statical approach, that's quantization over training, but you need to feed a little bit more data to the neural net. You can think of it about somehow like the second fine-tuning to make your model weightless. Yeah, so here's the table with quick results we got during the 2 months. So, yeah, the first column is the bare PyTorch implementation for inference for encoders, like that listed here. So this is the just bare BERT, distilled BERT, and 2 mini language models that is actually have less parameter than the distilled BERT and BERT. So yeah. So the first column is bare PyTorch. The second one is the built-in PyTorch quantization. So you can actually quantize the model like inside your PyTorch code for F16 only. The third column is the TensorRT engine. Actually, that engine not only quantized the model, but also made the pruning of the neural net and lots of optimization inside. And the last column, but the most interesting one, is the int8 Tensor runtime engine. But it's not out of the box. It's manual and handcrafted. Yeah. So the most interesting result is in the right and bottom cell. Yeah.
Sorry, I think I missed the point. So what these numbers represent here?
Yeah, that is the sequences per second.
Okay.
Yeah, the max length of sequences for this experiments is 256, I think. Yeah, and the batch size was varied from 228 to 512. So yeah, how we actually measure our quality of our models? We use the semantic spatial similarity. This is the part of blue benchmark. And that's the simple idea. You have 2 sentences. You encode them. After that, you just come the assign distance or similarity. And you also have the ground truth and the human markup. Human just decide whether these 2 sentences are similar and make the score from 1 to 5 with the 0.2 step. So after that, you just measure the rank correlation between them, and every single result from the previous table, the quantization from, for instance, bare PyTorch to Tensor runtime int8 didn't lose this matrix even for 1%. So yeah, there is no drop, no significant drop. You actually can control it, but we'll speak about it later. So yeah, so how can you reproduce the results? You can take almost any high-based model, because if your model has some custom layers, there's no way to do that without the handwritten interface for TensorRT or ONNX graph. So yeah, after that, you can make the serialization to ONNX graph. It actually looks like that. That is the ONNX graph. So after that, you can pass your graph to any runtime you want. So yeah, you can do the ONNX runtime. ONNX also has its internal runtime, but more for CPU actually. It's better to accelerate to CPU inference on ONNX runtime. Or you can choose the Tensor runtime to better performance, to high performance. You actually can see here the max length determined and the batch size. But actually here is the example that you actually can leave it to your runtime to determine what is better max length and batch size for the model to infer faster. After that you need to set up your executor and profiler and streams also, for data. And just make the inference. It's actually almost out of the box, but that results only for float 16 with TensorRT. If you want int 8 runtime, you need to customize lots of code. You need actually control that your drop of accuracy is not significant and so on and so forth. So yeah, here also the link with the pre-built Docker containers with Triton servers with accelerated GPU inference setup with lots of libraries like kubebus and stuff like that. So yeah, what else? Not only quantization for sure. So the pruning is the process when you just trying to remove redundant operation inside the neural nets. You can remove some redundant neural and connections that makes your nets like less computation. So yeah. So what else? The one more option is the distillation. Distillation is the process when you try to initialize the process with teacher model that is bigger, much more parameters than the student model, and you try to reproduce the result that teacher model can get. So your loss is the difference between the predictions, and you backprop it to the student model. So you try to train the student model by the mistakes from the teacher model. Yeah, actually the distillation is not the only one option to make your models smaller. You also can transfer some knowledge. For instance, you can make your student model multilingual, or maybe you can make it like sentence-based, not only word-based in Quadro. Yeah. So yeah, what else? There's lots of options actually. The interesting is you can take some other backends, not only the PyTorch. You can try different compilers that built for machine learning. You can try some libraries from Nvidia NGC that make the custom neural nets and layers for faster inference. So yeah, but anyway, to get the high performance like 100K sequences per second, you need to customize everything and work a lot. So yeah, what you can start with? You can start with vanilla PyTorch. It's easy. I don't overload any high-face model and just make the inference. You can enable the automatic mixed precision. That's built in PyTorch, as I already said. You can serialize your model to ONNX graph, and after that use the, for instance, ONNX runtime for faster inference in the CPU. Or you can try to put your ONNX graph to TensorRT to accelerate GPU inference. Hello. So, guys, actually we have one of the guys in the audience as a special guest. Ashot, please welcome to join me to discuss a little bit more about the theory of quantization and so forth.
I can, if the guys want, let's say, more examples of how this is achieved and what are the meanings behind all of the cool keywords that Vova has just mentioned. Okay, I'll jump in. So, just to elaborate a little more on what every point here means, so that's quantization. So, who has a clue of why quantization actually works? So, what's the benefit of this thing? We have less bits. Karen?
I mean, we don't need that kind of precision, right?
Yeah, but if we don't need that precision, what is that allows us to have higher performance but by reducing the number of bits?
Like when talking about quantization, we may even mean that we are using integers, right? Because integer operations are much faster.
Exactly.
And the same thing applies to much shorter floating point operations.
Exactly. So whenever
down to int 4 if need be.
Yes. So when we go down from floating point arithmetic to integer arithmetic, we get the benefit of being able to represent some of the arithmetical operations with less transistors. So if you take modern GPUs like the A100s, which are considered the state-of-the-art for AI training, what we generally have is a huge part of the die that is responsible for floating math arithmetic, and then we only have a few LUs, arithmetical logical units. So in the past, the logic, like the idea behind all of this hardware diversion was that CPUs are good in integer arithmetic, and then the GPUs are good in floating point math. So in the past, it would have been normal not to have any integer arithmetic on the GPU at all, and almost no floating point arithmetic on the CPU side. Now there's kind of a convergence back towards like similar kind of homogeneous architectures, and we start getting integer cores, let's say integer processing units on the GPUs as well. But even if we take, let's say, the A100, we open up the website, and unfortunately we don't have the technical means to show this on the biggest screen, we would see that they may suggest something like 300 tera operations per second for matrix multiplications in floating point 16 arithmetic, but also the kind of the same for U16, so which is unsigned integer 16 bits. So we kind of get the same performance number, but one of the big benefits here is that to get to this performance, we needed less space on the die. Less space means less transistors, less cooling, and we can actually feed more on the same chip. So if you look a little wider towards how machine learning is evolving these days, and not just the inference part, but the training as well, we're getting towards the age where we can have more brands of hardware, including companies like Graphcore or Cerebras and stuff like that, who would prioritize or can prioritize just integer arithmetic in case their software stack is ready to kind of transition and quantize the entire neural network. So this is kind of the topic that we wanted to discuss further with you later on the next meetups, potentially, maybe in August, like how quantization can be done during training as well. So how can you do quantization-aware training, the part that Vova mentioned here, like the last point. Then the dynamic quantization part here is a bit of a mislead. So dynamic quantization is like a very broad description. Every brand does it in a different way. In theory, like even in practice, even with GPUs, even though it says CPU only, you can have floating point cells, floating point cells and matrices, and then during the computation, the cast will take place almost implicitly, downcasting the float 32 number down to float 16, and then doing the matrix multiplication on the tensor cores with a TF32 precision with like the tensor flows described here. Then, in terms of specification and pruning, again, those two things also exist, both during training and outside of the training. And then the distillation part, as also you've mentioned, is kind of one of those things when you can have, again, a trainer for knowledge distillation, but also weight distillation. And then there's the last part, which we kind of missed, but it's one of those parts that you may use even more often. So if you take an engine like PyTorch, PyTorch comes with a bunch of bells and whistles you can configure the way you want. Including there's like a Torch script version, which is essentially an embedded JIT compiler for your pipeline. It will not work with every single model. It will not work with every single model, even from Hugging Face Portal. But sometimes it does. And it's not the only brand. So there are a lot of companies who exist solely for compiler level optimizations for machine learning pipelines. What do they do, aside from all the first 3 points we mentioned? They actually also understand how the hardware is built so that the software stack doesn't have to suffer from it. So one of the big problems that our company also often tries to solve is, let's say, memory bounds. So logic and compute is very cheap compared to memory accesses. But modern neural networks are too big to fit into the SRAM of the chip. So you have to fetch it from the video memory, from GDDR6 or HBM2, whatever runs your GPU. So the problem there is that even if we take the CPU numbers, the memory access can be 300 times more expensive than the computation, let's say the arithmetic of adding the numbers. So if the bottleneck is so severe, and if you have an ONNX graph like this, describing that we do one kernel and then only the other, it means that first we have a CUDA kernel, a CUDA program, let's say, that does an element-wise operation on every part of the matrix that you fed in. But then the kernel ends, the data is offloaded back into main memory, and then the second kernel proceeds doing another element-wise operation on the same data. So one of the simple tricks that compilers can do, but not every software package can do without going down to that level, is kernel fusion. So if you're doing element-wise operations and multiple layers in a row, it makes a lot of sense to actually load the data into the GPU registers on every single core just once, do all the operations you need, and then offload to memory once. It's kind of easy to do on the CPU side. It's much harder with custom accelerators, especially, let's say, AI hardware. And then there's a bit about these numbers that I can briefly mention before returning the mic back to you. Experiments are hard to maintain, especially data science experiments written in Python. So the numbers that are valid here may not be valid tomorrow or after tomorrow. Some packages might not even build, especially the ones that require custom configuration. So the numbers that you see on the right, in the right column, the TRT I8, it's kind of similar to the state-of-the-art numbers claimed on Nvidia's website for that benchmark. So whenever they release a new lineup of GPUs, they pick two reference cards. In this generation, it's A100 and A40, if I'm not mistaken, or A10, something small. And they kind of describe what kind of performance you can squeeze if you go all the way. So we succeeded in replicating those numbers. We are 100% certain that it's like not the absolute end. You can do a lot more research. It's just that modern packages do not do that. So we also did some more stuff with, let's say, TensorFlow. And with TensorFlow, what you get is generally performance that without custom configurations in PyTorch is similar. Sometimes the deployment is easier. And sometimes there will be, let's say, plus or minus 20% of variance. With PyTorch, at least from our experience, and especially with textual models, assuming that transformer library is built mainly on PyTorch engine, it's somewhat easier to configure faster backends. And even on our corporate portal, we sometimes describe the small bells and whistles people can configure in high-end packages, even in Python. So when you take NumPy, you can choose which BLAS library you run underneath. Same way here, you can enable some of the custom optimizations in PyTorch that are not enabled by default. And even if you are not going to downcast your float 32s into float 16, you can enable implicit procedures like that will happen behind the scenes in the engine itself. And in that case, so the number that is described here for PyTorch for F16, for MiniLM 6, I think you can get up to, let's say, 8,000 or 9,000 operations per second. With TensorFlow, we didn't get that far. Maybe that's the main points that I wanted to cover, just as a final notice. And then if you are certain that you are using only the most mainstream architecture, such as you are not going to use some form of a mini-LM or some specific sentence transformer, you are doing text, you only use verb-based uncased, probably the most downloaded pre-trained image on the Hugging Face portal. In that case, NVIDIA's and Tencent libraries might work out of the box. Not always, but that's generally the case. Okay, thank you very much.